Welcome to Train Signal. You are watching Configuring High Availability of Cisco UCS. So in this lesson we're going to talk about Cisco UCS and high availability, just kind of as a general idea and walking through some of the configuration options and how UCS handles high availability. So some of this will be review from other lessons, but kind of want you to understand that the blueprint for the exam specifically spells some of this out. And there's some information that really doesn't go with other lessons like split brain and fabric interconnect elections and things like that. So we'll start with UCS and high availability. Then we'll go through quickly connections, clustering, terms I want you to understand, and high availability for data. Then how the fabric interconnects handle elections, what happens with split brain, and then we'll do some managing high availability and a lab showing you how you can look at which interconnect is primary and how you can force that and switch that rotation if you want to. So Cisco UCS and high availability. By now you're probably aware that UCS is very highly available. There's pretty much redundant everything. Outside of a chassis or specific things on a blade, even though we can have backup blades with service profiles, everything that's really important is redundant so that a failure doesn't take anything offline. This lesson is going to walk you through managing all those high availability connections, features, and options. So first, there's my little diagram down at the bottom that I've shown in other lessons, but it really shows kind of this redundant nature. So as discussed, interconnects are connected to each other via Ethernet cables for UCS management clustering, L1 to L1, L2 to L2. You have one primary interconnect and one subordinate interconnect. The primary is primary for management. They're both active for data. You have one or more connections from each chassis to each interconnect, 1, 2, 4, or 8 with the new FEXs. So, most of the time you're going to want to do at least 2. You can do 1 and 1 and still be considered redundant because you can fail from one interconnect to the other. But usually when we do deployments, the minimum is 2. That way a single module, cable, anything like that doesn't cause the whole side to fail to the other side. But you can do it with 1, and this just shows you that there is redundancy between the interconnects and down through the chassis. So each interconnect is a separate entity. They both run in XOS and UCS Manager, but only one is active for UCSM at a time, the primary interconnect or primary node. The other is a subordinate. And as I've said many times, they're both active for I/O. And I repeat this often because it's kind of a misunderstood thing for a lot of people that are new to UCS. They hear cluster and they see we don't cross connect and they think that there's only one active at a time, but they're both active for data. The management port on each interconnect is connected to the same layer 2 management network. That's real important. You need to have them on the same layer 2 broadcast domain. Each interconnect has its own management IP, as we showed when we did the initial deployment, and a third shared cluster IP that floats to the primary interconnect. Remember that each FEX in a chassis goes to a single interconnect, and we've hit on this before. On the back of the chassis you have 2 FEX, 2 I/O modules. Each of those goes to a single interconnect. So if you connect the left FEX to the top interconnect, he only goes to the top interconnect. The right FEX goes to the bottom interconnect. You do not cross connect the FEXs to the interconnects. So a couple of quick terms, and these are kind of important. They're especially important if you're taking DCUCI exam. Cisco likes to hit you on terms. I guess everybody really does. But if you don't understand what they mean by node or group, you're going to be a little bit confused. So down at the bottom I kind of spell it out in a simple diagram. A node is one of the fabric interconnects. The primary node is the active interconnect for UCSM. The subordinate node is the non-active fabric interconnect. Both of the nodes together make up a group or a cluster. So within a group you have 2 nodes, one active, one standby or primary and subordinate. So UCSM clustering is active-passive, I/O is active-active, and you'll hear that asked a lot, and you'll see these terms come up. So node, group, active-active, and active-passive. Each interconnect has its own NVRAM or non-volatile random access memory that it uses to store data. Basically, if I flip the power off, the data still lives on the NVRAM. When both fabric interconnects are functioning, that data is replicated between them. Goes for configuration data as well as other things such as firmware images. So when we dump up firmware to the primary node, it automatically gets replicated to the subordinate node, so we don't have to do it twice. But when these guys are both up and talking, the data in the NVRAM is replicated between them. Now, each chassis management controller, CMC, which is the kind of management functionality that lives in a chassis, stores information in NVRAM about the chassis. It has a serial EEPROM called a CPROM, if you want to call it that, a chassis number, and each node or each fabric interconnect sees this information. So when you bring up a chassis, the first one you bring up is 1, second one's 2, third one's 3, that stuff gets written to this EEPROM. So if you disconnect it, reconnect it, he will come back as the same chassis. We'll talk more about this EEPROM here in a minute, but it is viewable by the fabric interconnect, readable and writable to store information about that chassis. When the fabric interconnects come up, there's an election. So, one of them has to be primary and one of them has to be, as a subordinate. So, they have an election and one is designated the leader. And this doesn't change unless there's a major disruption. And what's really interesting is, in fact, you can have an FI actually reboot and still maintain leadership. The reason being is there's some things the interconnect, the primary, does that's runs the show, and it's less disruptive or intrusive to the environment for a quick reboot not to fail that over to the other interconnect. The idea, reduce disruption. So normally a new leader is not elected unless the current leader just outright crashes or we administratively change and force it. And you usually do nothing for this process. So it's usually automatic and it's inconsequential who is the leader. I mean, it really doesn't matter. In fact, you don't know unless you go look. And I can fail them back and forth, and I/O still runs. There's nothing causing a disruption there. If the FI flat out crashes, that's going to disrupt I/O. It's going to fail things over. But, moving the leader or the primary back and forth does not disrupt I/O. So it's not really important to understand how there's an election. In fact, it's not even really that well documented. Just understand that one is primary and one is subordinate. So configuring node high availability. So you remember when we did the initial configuration, it said, hey, are you creating a cluster? Yes or no. When you answered yes, you configured node availability. It's just that simple, really. The only other thing you had to do was connect the cables properly. L1 to L1, L2 to L2 if not. And I've repeated that like 100 times as well, but I see it commonly misconfigured. So if for some reason your interconnects aren't seeing each other, HA is not functional, check those connections. But really that's it. Initial configuration, we say yes, we're creating a cluster. Then when we bring up second interconnect, we say yes, join the cluster and give it the password, and that's all there is to it, assuming that your HA connections, your cross-connect cluster connections, are done properly. So what happens if split brain occurs? So split brain is when both interconnects think they are the primary or active in the cluster. They both think they run the place. And so, there's a couple of things that might cause this. Really, there's nothing as far as a normal failure that should cause this. So, but what could? So the first one is if the interconnects cannot communicate over layer 2 or layer 3. Basically, they're not talking between the two cluster connections, and they're not talking between the two management connections. You basically have a really bad failure. And since you really should just literally cable L1 to L1 and L2 to L2, not go through a switch, this is exceedingly rare. I mean, you're going to have a switch failure for the management, and something's going to have to happen to those cross connections. And usually this is administratively done. Someone unplugged things they shouldn't have. But if that happens, this is known as a partition in space, meaning they literally can't make the jump across the air to talk to each other. The fix for this is really easy. Plug your cables back in. But just confirm why you had this sort of a failure. The second type is one fabric interconnect may have a newer configuration that was not replicated to the other. So you may have had an interconnect down. Someone made changes to the UCSM configuration. They then shut that interconnect down and brought the other one up. And so now what happens is the interconnect goes and looks at that EEPROM on the chassis. He goes and looks at the EEPROM and he says, weird, I am configuration revision 118. That chassis says the last one he saw was 124. So all of a sudden I'm very confused. And that's known as a partition in time because he's kind of living in the past. And so to resolve this, the interconnects use that EEPROM that's in the chassis. And they can look at configuration information there, read it back, and kind of get a state or an idea of what state they should be in. So they both use the EEPROM, and both of those causes are resolved in a similar fashion. For a partition in space, meaning the cables are disconnected, the two interconnects just aren't talking to each other, they do what's called a quorum race. So they go look at a chassis, and I believe it's chassis 1 where they do this, and they write to that EEPROM as fast as they can. So as soon as they figure out there's a weird problem, and I'm not talking to the other guy, they both try to write to that EEPROM as fast as they can. The first one that writes wins. He becomes active. The other guy sees that the other interconnect has written, understands that he's alive and well, and he aborts and backs out of the cluster and basically goes offline. When you connect the cables again, he'll rejoin and communication comes up. So it's what's called a quorum race. They write to that EEPROM. For a partition in time, the primary node writes a number to the EEPROM. So he writes kind of a configuration version. If the primary node is down and the subordinate tries to create the cluster, it first looks at what he thinks the configuration revision is and then looks at the EEPROM. If he's got a newer version than what's on the EEPROM, he comes up, writes the config, and everybody's happy. So if he comes up with revision 150 and the chassis has 112, he knows that he's newer than the chassis and he can dump that down, and the cluster will come up and everybody's happy. But if he comes up and he's got revision 110 and the chassis has 150, then he thinks there's a problem. I don't know what current configuration is. I'm going to cause more problems than I'm going to solve. So basically the cluster does not come up. You can look at the console, it'll tell you, and the cluster just doesn't come up. So then you need to bring the other primary node back online to kind of stabilize the cluster, then bring the subordinate, let them replicate, and everything will be good. But in the end, the idea is that the CPROM is what kind of resolves the conflict in a split brain. It is the single quorum that both interconnects are connected to, and therefore that's kind of the shared medium for passing information. So occasionally you may want to flip the status of the nodes. Maybe you're going to bring a node down. We'll show you how, maybe you're going to update firmware and you want to flip it and update the firmware on the other one. So there's two types of promotions or demotions. So there's a switchover. This is when the administrator says, I want to flip you guys, and it's sometimes called a synchronous request. So it makes the subordinate primary and the primary subordinate. It just switches the roles. It's kind of like asking nicely, hey, do you guys mind flipping because I got to do some maintenance? And again, it's called a synchronous request. Then there's failover. Calls by UCS manager and promotes the subordinate to primary. It's called an async request. Usually this is bad. Usually there's a problem. Usually it's something has happened to the current primary and UCSM sees it as bad enough that he needs to fail the cluster over himself. You can force a switch over and monitor the HA status using the CLI commands that I'll show you here in just a second. So let's quickly jump in the lab. This will be a pretty quick lab. We're going to check the cluster status, then we're going to ask nicely to change the primary node, and then we're going to kind of force the issue and force a primary node change. So with that, let's go ahead and jump on over to the lab. So jump over to my remote desktop session here into my lab, and we'll start off by launching PuTTY. Choose the UCS server in Greensboro, and we will connect in. So I'll log in as admin and do my password if I get it right, and there we go. So I'm going to tell you right now, a quick and easy way to see who is your primary interconnect is to look at the prompt. So as you remember, when we did the initial configuration, we gave everything like a cluster name, and then for one of the nodes it was -A, for the other it was -B. The one that answers when you SSH or telnet in to the command line interface, in this case B, is your primary, because he's the one that holds the cluster ID. So you can do things where you can telnet in or SSH in specifically to an IP, but if you go to the cluster address, you're going to see that it's going to be, the one that has the currently as a primary is going to answer. Show cluster state. So that's the simple command. So we do a show cluster state, and it gives us a couple of things. First, it gives us a cluster ID, which is not something you usually need to worry about, but there it is. And then it says who is primary, in this case B, and who is subordinate, in this case A. And it says HA ready. That means the two interconnects are talking to each other. So if one, if B should fail, A will jump in and take over for UCS management. And if you look up there when I did show cluster, the other option is extended state. So extended state starts by basically giving you the same thing as first, and then giving you some more information. One thing here that I didn't talk about was last election time. So anytime there's an election, it will show this information. That way you can see if a change occurred. But it shows B is up in primary, A is up in subordinate, and it gives you some other information. Member state is up, lead state's primary, management services are up. So you want to see up, 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 and primary and subordinate. Heartbeat state, primary is okay, that's good, it means that cluster link is working, and internal network interfaces ETH1 and ETH2 are both up. So that's exactly what you want to see. HA ready. And also, if you remember earlier here, we talked about what happens in the case of split brain scenario, and I told you that it used the EEPROM on a chassis. So right here it says detailed state of the device selected for HA storage, chassis number 1, and it gives you the serial, and it tells you if it's active. Now I've only got one chassis here in the Greensboro lab, so odds are it's going to be 1. But if you want to see which chassis it is and confirm it, because maybe you pulled chassis 1 out, added things back, moved some things around, that's a good way to see. So now that we've looked at what the status is, let's take a look at what we need to do to kind of fail it over. So to do that, you'll need to connect to local management. We'll do that, and it kind of goes under layer and does local management on the cluster. And then the commands are just cluster commands. So we've got 2 commands. So we can do lead and force. Lead is the way we ask nicely. So if I want to say, hey, I really would like A to take over as primary and B to go to subordinate, we use the lead command. This was, we talked about that a minute ago, where we basically flip the interconnect. So let's do cluster lead. We do question. It says, which one do you want? Well, right now B is primary, so we're going to flip that to A. And you're going to notice something happens when I do this. It's going to say OK, and then it's going to kick me out. Now, why did it kick me out? Well, it kicked me out because it just moved the IP from one interconnect to the other interconnect, and then my connection dropped when that happened. So what I can do is go up to PuTTY and say restart session. That reconnects me to the same IP. The fact it asked me for login is a good thing. It means everything came back up and everybody took over. Type in my password, and we should see the prompt change to A, which we do. But if I do a show cluster extended status or extended state, we see that the roles have been reversed. I also see that, if you were paying attention or I'd mentioned it to you, that the time updated when everything flipped over. A is up in primary, now B is back to being subordinate. So that's the quick and easy way to fail things over. But what if you want to force it? What if I want to, there's an issue and maybe primary is having a problem and I want to force the subordinate to take over the primary role? Well, to do that, use the same command we just used. So we want to connect to local management. And then we use the cluster command, but this time we use force. Now, I'm going to tell you right now, this isn't going to work. It's not going to do any damage, but it's not going to work since both interconnects are up and I'm connected to the primary. But if I do force primary, and really what this does is it says, I want you to take over, whichever interconnect you're on is going to take over primary role. And if I do that, it's going to probably tell me, yep, the election was successfully completed. So it's not even going to attempt that right now because, hey, I'm up, I'm talking, we had a good election, everybody's happy. But if for some reason, you were in a worse state and the election wasn't completing and you really wanted the other interconnect to take over, you use the cluster force primary command. So as you can see, this is really simple. You don't need to log in to CLI to see the state, by the way. I believe I've shown you that in an earlier lesson, but if not, let me task back over and I'll launch UCS Manager, open. And this will be against the 1.4 UCS platform emulator again. Log in as admin, since I've left it as default. Go ahead and jump into UCSM. And from here we can go down into the equipment list here and look at the 2 interconnects. So go to Equipment, Fabric Interconnects, Primary, and it tells you right here, primary or subordinate. And this one shows that it is primary. And I believe if you look over High Availability Details, leadership is primary, cluster link status, it's not talking to the other side. So that's one thing there. But that's a quick and easy way to see it actually from UCSM. And if you notice, there's really nothing you can do to flip this over from within the GUI. So I think it would, to me it would be nice if they would let you kind of flip those over within the GUI itself. But I guess this is one of those things to where, Cisco doesn't really want you kind of doing that and clicking that button, even though it's not really disruptive because you're just failing the management functionality, not I/O capability over. It's just one of the things that Cisco does. That's it for this lab. So again, remember, CLI you can do show cluster state or extended state, and then if you connect to local management, you can do a cluster lead to ask nicely to fail the interconnects over, or cluster force primary to fail the interconnect that you're on and force him to be the primary in the cluster. And then you can log into UCSM and see primary or subordinate right there. So let's jump back to the slide deck. And so that's it for this lesson. Pretty short lesson, but it's good to know. These are questions I get a lot, especially around availability and connections and clustering. And I know I've told you like 100 times about UCSM clustering against the I/O active state, but it's a topic that comes up. And to be honest, it's a topic that is asked about on the exam from my experience. So it's spelled out pretty clearly, I believe, in the blueprint. So it's good to know those things. So first, we just kind of did an overview of UCS and high availability. Just gave you kind of the general concepts and ideas. We showed you the diagram, talked about really everything except down to the actual chassis itself, or maybe a specific blade is redundant. Then we looked at the high availability connections, so the redundant connections from the chassis to the interconnects, between the interconnects, and up to the rest of the network or to the storage. High availability clustering again, active and standby or primary and subordinate for the two interconnects, even though I/O is active across both. Terms, node, primary node, subordinate node, cluster group or just group, those are kind of important. I'll tell you, that's kind of some of the terminology they use on the exam. And it's a kind of terminologies that you don't see outside of a lot of Cisco specific material. So I think it's only fair to kind of enlighten you on some of the terminologies that they use when they're talking about these things, so you understand what it means when it says node or what it means when it says group. Then high availability data. This is kind of the counterpoint to the high availability clustering, where clustering again is primary and subordinate, but for data it is active, so you can have both interconnects, both functioning, both passing traffic at the same time. Quickly hit on interconnect elections. I know we didn't go into a lot of detail on that, but that's really not well documented. And really, it's not something you have to understand to that sort of a level. It's not like, if you're a network guy, it's not like a root bridge election and spanning tree, or even in the Windows world, talking about master browser elections and things like that. It's just between the two interconnects and the two interconnects only, and it's only for management. Then split frame. So we talked about that kind of partition in space and partition in time. Partition in space being when the interconnects can't physically talk to each other, layer 2 or layer 3, because somehow you've amazingly lost those cross-connect cluster cables and the links up off of the management ports. And then we had the partition in time, where maybe one of the interconnects was offline for an upgrade or something. The other one made some changes to the configuration, and then you for some reason took that guy down and brought the other one back up, and the configuration set was out of alignment. So the way we fix that is UCS uses a chassis and an EEPROM called the SEEPROM, SEEPROM, on the chassis, and they kind of do a quorum race. So if it's a partition in space, they do a quorum race to see who can write first. Winner gets to be the primary, the loser backs out of the cluster until communication is restored. And then you've got your partition in time fix, which is every time you do a config update on the primary node, it writes a kind of a version number down to that CPROM, which when the other node comes online, looks at that. If the configuration he has is less than what's the version number written on the CPROM, the cluster does not come up. So you're not going to be able to really manage anything. So you're going to need to resolve and fix that. Then finally, managing high availability, just what we did in the lab a second ago. Managing the cluster and node failover, looking at the state of the cluster and the extended state, and then asking nicely to do the a synchronous or an asynchronous sourcing of the cluster failover. So again, kind of a simple lesson. It's something that we've talked about in pieces and parts, or really more than that in some of the earlier lessons, but it's important to put it together because these things are spelled out directly on the exam. Plus, it's a lot of questions that I get, especially talking about architecture, especially people that are new to UCS, and they want to know what happens when things go wrong. So hopefully that clears a lot up for you. Hopefully you enjoyed that, and I'll see you in the next one.